just a reminder that you have an exam this Thursday. And next week, next Thursday, we're going to have a quiz. And then the following week, we're going to have another quiz. We don't have a final exam. We just have 2 more quizzes after this exam. Sam, you have a question. I'm going to ask you to hold on to your question. At the end of the day, if we have time, I'm going to give you the opportunity to ask your question. If not, you can ask them on Thursday. Is that okay? So if you have any homework questions, feel free to come see me during office hours tomorrow, or ask them on Wednesday, or come to office hours on Thursday. Just like before, we're going to try to, on Thursday, we're going to try to spend about 20 to 30 minutes to go over any final questions before the exam, and then you have 1.5 hours to work on the exam as before. What does it cover? So there's a question, what does the exam 2 cover? If you go to the website, which section was it? Was it 7? Double check. I'm not I don't remember exactly. I think it was a 7.4, 7.5, 7.8, and then 11.1 to 11.4. So part of the material we talk about today will be on the exam, but part of it will not be. I'll let you know when we get there. Okay, so that's a coverage. Any other questions about the exam or next week's quiz? This is we have 2 more weeks after this week, right? So the class ends on July 29th is the last day. We're almost at the end. All right, so let me begin by going over one example on comparison test. That's what we did last time. So 11.4, we talk about direct comparison test. Right, so just a kind of a review. The example I have is we want to know if the series is convergent or divergent. And from 1 to infinity, n squared plus 2 divided by n to the 4th plus 5. Is this series convergent or divergent? That's what we want to know. If you remember that comparison test is that we take the series we have, and then we try to find another series that's either going to be bigger than this or smaller than this, but it's easier to compare, right? Most sort of fundamentally, the basic idea is that we take the formula for the AN term formula. We're going to find something that's simpler than this one. So here, because of the numerator and denominator both adding a number, to me, when I look at this, is that I see that n squared plus 2 over n to the 4th plus 5. If I lose a part that I'm adding to the denominator, for example, if I'm losing the 5, right? If the denominator gets smaller, the values actually get bigger, right? If I drop the adding 5, so the denominator is getting smaller, but the overall fraction is getting bigger. So this fraction is less than or equal to n squared plus 2 over n to the 4th. I could also drop the part in the numerator, but if the numerator gets smaller, the overall fraction is getting smaller, right? If we keep the denominator the same. So I can write as n squared divided by n to the 4th plus 5. But if you're familiar with this, so we want to know the series, right? We want to know whether this one converges or diverges. So you can either pick the one that's smaller or the one that's bigger to work with. By just inspection, for me, I'm going to begin with the one on the right, because that's a little bit easier to find the sum of that series. So we're going to use the one on the right. So let me write down, since we have n squared plus 2 divided by n to the 4th plus 5 is less than or equal to n squared plus 2 divided by n to the 4th. Therefore, for all n, therefore the series from 1 to infinity, n squared plus 2 over n to the 4th plus 5 is going to be less than or equal to the series n squared plus 2 over n to the 4th. Right? And then the next step is we just focus on the series that's bigger. We want to know if that's convergent or divergent. So let's take that one and focus on it. So how do we find if this series is convergent or divergent? Well, there was a few tests that we could do, right? We could try to use a divergence test to show if it's divergent. It turns out that from that test, we cannot conclude. You can try that. So let me just try divergence test. You can also try the integral test. And that's also called the P-series test, right? You can try that. Well, we cannot try P-series test directly because that requires we will have something like 1 over n to the p. That's not in the correct form because the numerator has a additional term positive 2 there. So that doesn't work directly. But if you remember that a couple of lectures ago, we could take the series and split it into the sum of 2 series. So I could take this one and then write it as sigma n squared over n to the 4th plus sigma 2, just a positive 2, divided by n to the 4th. If we split that, so maybe I should take 2 steps. So what I did is I split the fraction into 2 fractions first, and then I split the series into 2 series. So that becomes series n squared over n to the 4th. That's just 1 over n squared plus series 2 over n to the 4th. So now I can focus on each one of them to determine if they're convergent or not. Each one of them satisfied the P-series test. So this one P equals 2, which is greater than 1. If you recall that if P is greater than 1, then the series is convergent. So this one on the left, so this part is convergent. And the second series, even though there's a 2, I can bring the 2 outside and then write as 2 sigma 1 over n to the 4th. The P is 4 here. Again, that's greater than 1. So this is also convergent. And if we're adding 2 convergent series, there's a theorem we talked about briefly in the past that when you add 2 convergent series, the sum is also convergent. So going back, this series on the right, this is convergent, right? That tells us that the big sum, the big series is convergent. Therefore, the one that's smaller than that series has to be convergent as well. So the one that we are interested in, this one on the left, is also convergent. That's a comparison test. In it, we use comparison test to begin with, but at some point, for the series that we can find it easily, we use P-series test twice to determine if that one it's convergent or not. Okay.
So if one of those terms that we found on the bottom was divergent, that means the entire thing is divergent? Or correct. We can't conclude?
I have to think because we're going to talk about something slightly different today. that might contradict with what I'm going to say. I'm going to say that if one of them is divergent, then the sum of those two series together is divergent. Because if it's convergent, the sum, so if you, let's say you have a series AN and then series BN, you're adding together, right? Let's see, this one is convergent, this one is divergent, which means that this sum is going to be finite. This sum is going to be infinite. Whether it's positive or not negative, we don't know, right? It could be plus minus to each one of them, doesn't matter. If you take a finite number, you add it to an infinite number, it's still going to be infinity, right? And if you take a negative finite number, add it to a positive infinity, it's still going to be infinity. It doesn't matter which one is positive or negative. Finite number is always smaller than infinite. So when you add to an infinite number, it's always going to be infinity. Good. That's a very good question. So convergent series and the divergent series you add together, you get divergent series. Good question. So that's a comparison test. Just keep in mind that you might end up using multiple tests in the process. So the next thing I'm going to talk about, any questions before we move on? All right. So the next thing is also in the section 11.4. You have to know this, and that some homework questions are based on this part. So part 2 is called limit comparison test. So let me write down the test itself. So this is on exam. So the test says, suppose we have two series, series AN and series BN, with AN greater than or equal to 0, BN greater or equal to 0 for all n. So for all the terms that in the series is always going to be greater or equal to 0. We define a constant C. The C will be limit n goes to infinity of the ratio AN over BN. So we basically take the sort of the last term, or it's infinite, so we don't have a last term, right? The infinity, the very last term in that infinite series, we take the last term of the AN series and the last term of the BN series. We find the ratio, find the ratio, we call that C. That's what this limit n goes to infinity means. So the theorem is, if the ratio with the limit n goes to infinity, if C is positive and finite, so if the ratio with the limit is it's a value that you can find and it's positive value, then either both series converges or diverges. So this limit comparison test it doesn't, it just says, you know, if you have two series, the ratio of the term as n goes to infinity is positive and finite, then both of them will be convergent, or both of them will be divergent. It doesn't tell you exactly, you know, whether they're convergent or divergent, but they behave the same way at the same time. That's what this one says. So when do we use this? Well, to use this test, for example, I'm going to give you this example, is this series 1 over 3n minus n, and go from 1 to infinity. Is this convergent or divergent? Right. So here we only have one series. So this is only one series, and this is an. I just call this an. Right. If you only have one series, you cannot define a ratio C because you don't have a second series. So you cannot apply this limit comparison test. So if you want to use this test, you have to kind of pick another series and then use it with this one. So we need to use a second series. So that's what we need. We need to find the second series, and then we need to use it with this given series to determine if the given one is convergent or divergent. And then we need to find a second series that's simpler and easier to find the convergence. So how do we find a second series? So this is the trick that I sometimes use, but it doesn't work with all cases, but it works, you know, for some cases when you have fractions. So for me, I sometimes use just the leading terms of the numerator and denominator and use that to create a new series, and to use that one as a second series. So in this case, in this example, the numerator only have one, so just one, right? And then the denominator has two terms, 3 to the power n and then n. As n goes to infinity, if you kind of just look at both parts, 3 to the n will increase a lot faster than the constant n, right? So the leading terms of numerator and the denominator gives 1 in the numerator, and then denominator will be 3 to the power n. So that's the leading term as n increases, right? The one that we're subtracting, that doesn't grow as fast as 3 to the n, so it's not leading the behavior of the denominator, so we just ignore that. So the second series in this example will just be series n from 1 to infinity, 1 over 3 to the n. So this will be the second series that we need in order to use this comparison test. So that's the first step, is to find the second series that's convenient to use. So that's that part. And then after we have the second series, we have a bn that we can use, which is just 1 over 3 to the n. And the an is already in that given series. So now we're just going to follow the test says we need to define a c. So define a constant c that will be limit n goes to infinity, the ratio of an to bn. So that's a 1 over 3 to the n minus n. Oh, I probably didn't do it right. I did it all wrong. Not all wrong. We did most of it wrong, or most of it right. Some part it wrong. Let me take a step back. So the one that given, I'm going to call it Bn. And then the one that's come up with that's simpler, we're going to call it An. And then we're going to take the limit of An over Bn. That way it's easier to take the limit. So that will be limit n goes to infinity. An is 1 over 3 to the n, divided by Bn, 1 over 3 to the n minus n. And the next is just follow this to take the limit and to find c if possible. So that will be 3 to the n minus n divided by 3 to the n. And the split that was the limit, obviously. And to split the fraction, so that becomes limit n goes to infinity of 3 to the n over 3 to the n minus n over 3 to the n. As n goes to infinity, the first term is just 1. So this part becomes 1. But what about the second term? Well, the second term, when we take the limit, we might have to use L'Hopital's rule. So let me write down. So limit of the first term is just 1 minus limit of the second term, n over 3 to the n. We have to use L'Hopital's rule here. That will be 1 minus limit L'Hopital's rule. So we take the derivative of the numerator, which is 1, derivative of 3 to the n. That's 3 to the n times natural log of 3. Right, that's just a special rule to take the derivative of 3 to the n or 3 to the x. So just in case you don't remember, so note d dx of a to the x is a to the x times natural log of a. That's just the special rule I'm applying here. And if we take the limit as n goes to infinity, the denominator 3 to the n will go to infinity. So we got 1 over infinity. So that becomes 1 minus 0. So that's just 1, which is the limit. That's also the c value. So therefore, c equals 1, which is positive and also finite. Right? So we found out that the c we defined using the series an, the new one, and also the bn. We found out c to be positive and finite. According to this test, then we can say both series, so both 1 over 3 to the n and the series 1 over 3 to the n minus n, both are convergent or divergent, but we don't know whether they're convergent or divergent. And the next step is to find out whether they are convergent or divergent. Well, how do we find it? This one is the one that I'm interested in. I want to know if this is convergent or divergent. I don't know. So now we just know that this one and the new one both are convergent or divergent. So what we're going to do is that we're going to use the new one that we used from from earlier. We're going to determine if this one is convergent or divergent because this one is simpler. So if you recall that 1 over 3 to the n, as n from 1 to infinity, this one we can find out that this series here, I believe it's convergent. So we can use the, what was it? We can use the integral test to find out 1 over 3 to the x dx. If we carry out this integral, this improper integral, we're going to end up with finding that it's a finite value, I believe. limit t goes to infinity, 1 to t, and then 1 over 3 to the x dx. Yeah. I think I'm going to skip some steps because that would be a good practice for you to kind of find the antiderivative of 1 over 3 to the x there. So it turns out that this limit is going to be a finite number. And therefore, going back, this series that we are interested in, well, the improper integral is going to be convergent. Therefore, the series is convergent. So since the series 1 over 3 to the n is convergent, and earlier we conclude that both of them are either convergent or divergent at the same time. So one of them is convergent, therefore the other one has to be convergent. Because both are convergent or divergent at the same time. So that's what this test is. So there's a lot of steps you have to do if you try to use this comparison, this second part of the comparison test. You have to find the second series to apply, find out the C value if possible, and then you have to take the simpler one, the one that you come up with, to determine if the given series is convergent or divergent. I hope I didn't confuse you. Any questions on this one?
So I'm a little confused. After you found that C equals 1, what was your next step?
So after we found out C equals 1, that based on the test, that only tell us that both series, the series AN and the BN, both are either convergent or divergent, right? We don't know if it's convergent or not. That just tell us that both of them behave the same way. So after that, I have to determine if the given series is convergent or not. I can't work with a given series because it's not easy, right? So what I did is I work on the simpler one, this one that I picked. That one is simpler, so I took that one and I try to figure out whether that series is convergent or divergent by using the integral test. So I turn it into an integral, and then I write the improper integral using the limit definition. And I didn't finish everything, so I sort of stopped there and then let you finish. That'll be a good practice for questions that might be on the exam. So if you carry out this process, you're going to find out that when you take the limit, you end up with a finite value, which tells you that the improper integral, this one, it's convergent.
And that's the integral test we did, or what test is that at the bottom?
This is the integral test to determine if this simpler series is convergent or not.
Okay, thank you. That makes sense.
Yeah. And after we conclude that the simpler series, the one that I picked, this one is convergent, then, since both of them behave the same way, if one is convergent, the other one has to be convergent. Question. So again, this is another example that it's you need to use multiple tests to to look at the series, try to determine the convergence. Just like the previous example, we use multiple tests. Here we use 2 tests, right? One is not enough. Any other questions? I know that, I assume that most of you have not seen any of those in the past. I mean, you might have, but doesn't matter. So this is probably like new stuff to a lot of you, like you haven't really seen convergence test or just convergence divergence in the past. That's normal. So if it's confusing to you, don't panic. Just try to practice. Work on the exercise questions and then, try to understand the examples. Trust me, it's not easy for most people, especially if it's new to you, but don't panic, you're going to be okay. All right, I'm going to give you a second example on this. So the second example is this series, again, from n from 1 to infinity. And we have 4n squared plus n divided by square root, cubic root, cube root of n to the 7th power plus n cubed. Right, so this is the series that we want to know if it's convergent or divergent. So again, here we only have one series. So this one, I don't know, I'm going to call it AN or BN, but I'm going to leave it for now. Oh, okay. I just realized that I have not worked out this problem yet. I feel like I'm going to make mistakes here. Let's see. Hopefully not. Let's see. So for this series, I'm going to try to use the comparison test, the first part, the first part that we talk about. Wondering if it's going to work. You know what? I think I'm going to stop here because I have not done this problem yet. So by just looking at it, I'm not sure, but I'm going to come back to this example. Sorry about that. I don't want to do some wrong work. So the example is that this example is that we're going to try the second series and from 1 to infinity. And I'm going to pick the leading term of the numerator and the leading term of the denominator of this given AN or BN. So the leading term of the numerator is just 4n squared. The leading term of the denominator is just cube root. It's always cube root. And then n to the 7th. So that's the expression. That's the second series that we're going to use. You can rewrite it as n from 1 to infinity of 4n squared divided by 3 n to the 7/3. And then we can simplify this a bit. That will become series n from 1 to infinity. 4 is just 4. So n squared divided by n to the 7/3. That's 1/n to the 1/3 after we simplify the n terms. So this is the the AN. This is, I'm going to call it BN. And I'm going to stop here. So we're going to define a C, which is going to be limit n goes to infinity AN over BN, which is just going to be limit 4 over n to the 1/3 divided by the Bn, which is 4n squared plus n divided by cube root n to the 7th plus n cubed. So I'm going to stop here because I'm not confident that on the spot I can solve everything correctly. But I'm going to work on it later and then come back to this example tomorrow. So if you're interested, you should try to finish it on your own. See if it works. Anyone else have any comments about this example? Is there any other approach that we can take?
Can you not use the P series when you have that 4 times 1 over n to the 1/3? That's just the only thing I see.
Say it again.
Can you not use P series when you like split it up and have 4 times 1 over n to the 3rd?
Yeah, we can use the P series, right? So over here so for this series, if we want to know this one that we picked, right? If we want to know if it's convergent or divergent, we can definitely use P series. But that only tells us that the one we picked is convergent or divergent. It doesn't tell us anything about the one that we are interested in at the beginning. So this one is the one that we are interested in. So we have to use the comparison test. We have to use this C to determine if both of them going to be convergent or both of them can be divergent. That will depend on the value of C. If C is infinity, then they don't have any relationship, right? One could be divergent, one could be convergent if C is infinity, or if C is negative. So we have to show that C is positive and finite, so that we know that both series behave the same way. And then, you know, from the P series, we know one of them is, I think it's divergent in this case, then both of them will be divergent. So we still have to show the work for the C part. So you're right, we do need that at some point, but that's like later on. Okay, so you can try to find the limit there. Oh, actually, you know what? Let me take it back. Sorry, I'm a little bit, you know, underprepared today. Thinking maybe we should just carry out. I'm going to try this, but no guarantee. I apologize if I do make mistakes in the process. So we need to take the limit of this. So I'm just going to simplify this fraction. So that's a limit 4 over n to the 1/3, and times the reciprocal of the denominator fraction. So that's 4n squared plus n, and the numerator is cube root n to the 7th plus n cubed. And then that is going to be limit. The 4, I'm going to bring it outside. It doesn't matter where the 4 is. So bring the 4 outside. So we get cube root of n to the 7th plus n cubed. And then the denominator, we have n to the 1/3 times 4n squared plus n. So we have to distribute to each of the term there. So that's n to the 1/3 times 4n squared. That's a 4n to the 2 is 6 over 3, so 7 over 3. And the next term is 1 plus 1/3, so the n to the 4/3. and then that becomes 4 limit n goes to infinity of this expression. And I'm just going to take a shortcut. How do we take the limit of this? So we have to divide by the leading term of the numerator, which is going to be cube root of n to the 7th. In the numerator, as n increases, I'm going to take a shortcut here. So n to the 7th in a cube root, so that will dominating the behavior, right? Because n to the 7th increase a lot faster than n cubed. So in the numerator, I'm only going to consider the term cube root of n to the 7th. The denominator, n to the 7th thirds increase a lot faster than n to the 4 thirds. So I'm only going to focus on this term in the denominator. So that's 4n to the 7 thirds. This is like a shortcut, obviously. So that's a 4 limit n goes to infinity, and the numerator is n to the 7/3. Denominator is 4n to the 7/3, I think. So that cancels out. The n term cancels, give us just 1/4 in the limit. So we end up with 4 times the limit of 1/4. So just 1. Oh, that's not too bad. I'm lucky to get this right, I think. Double check. So this term and this term, they cancel, give you 1. Right. So we end up with 1 as a value for C, which is positive finite. Right. If that's a positive and a finite, that means we can apply this comparison test, conclude that both series, the one that's given and the one we picked, 4/n to the 1/3, and the series that we're interested, 4n squared plus n over cube root n to the 7th plus n cubed. Both of them are convergent or divergent. We don't know yet, but both behave the same way. So that's the using the C, or we pick a series first by using the leading terms, and then we define the C and find the C value. And then the next step is what Aiden said. So since both of them behave the same way, we have to know whether they are convergent or divergent. The one that I'm interested in, this series, I don't know, I can't find the convergence directly, right? If I can, I wouldn't go through all the trouble. So let's focus on the one that's easier. So this one, this series 4, I'm going to bring outside 1/n to the 1/3. This one, we know that using p-series test, like Aiden suggested, so here P is equal to 1/3, which is less than 1. Therefore, this series is divergent, right? So that's what the p-series test tells us. So this simpler series is divergent, but both of them behave the same way. Therefore, the other one that we're interested in is also divergent. So since the series 4/n to the 1/3 is divergent, and both series are either convergent or divergent at the same time. So one of them is divergent, therefore the other one, the one we are interested in, over cube root n to the 7th plus n cubed, is divergent. I apologize if I confused you a lot at the beginning. I think the work I did with the C is right, but double check with taking the limit.
I'm sorry, I'm just a little bit confused with that, like C equals 1 is telling us. I know that it's the same behavior, but what does that mean?
It just means that both series, the one that's given, so the one that's given is this one, and then the one that I picked, that just if C is positive and finite means both series are going to be convergent at the same time, or they are divergent at the same time, but both have the same convergence. That's what the C tells us when C is positive and finite.
So if it was negative, what does that mean? That they wouldn't be the same?
They wouldn't be the same. So one will, if C is not positive and finite, then they don't behave the same way. Like one will be convergent, one will be divergent.
Okay, that makes a lot more sense.
Yeah, if C is infinite or C is negative, so maybe I should write it down. So if C is infinite and or negative, we cannot conclude that both are convergent or both are divergent. So this test basically is useless in that case. So if we end up finding C is infinite, you know, you have to use a different test. This test is not going to be helpful. In that case.
Can you scroll up for a second? I had another question.
Mm-hmm.
So ultimately, how did you get that 4n7/3 on the bottom? I thought it was going to be 4n2/3. I'm a little bit confused how you distributed that. When we have the limit at the right side, 4/n to the 1/3 times that main thing we started with, or the reciprocal. Yep.
Right. So how do I end up with the denominator here?
Yeah.
So what I did is so just looking at the denominator, so I have n to the 1/3 times 4n squared plus n. So I distribute into each one of them. The first term would be 4n to the 1/3 times n squared. And the second term is n to the 1/3 times n. When you multiply those two together, you basically just add the exponents. So that would be 4 to the n raised to the 1/3 plus 2. So that will be the new exponent.
Oh, okay. That makes a lot more sense. Okay.
Same thing with the next term. You add the exponent. That will be 1/3 plus 1 in the exponent.
Thank you so much for explaining that.
Yep. Yeah, that's so n is just like x here, right? So if you have x squared times x to the 3rd, you just end up adding the exponents. Okay. So questions? Any other questions? So I give you like I forget like probably 5 questions in the homework. So if you try the homework and you couldn't do it, probably because those problems. So if you go back to them and try to look at the examples I went over today, and hopefully that will help a bit on the problems that you couldn't finish. All right. So that's all the material that will be on the exam. So the stuff that I'm going to cover next is not going to be on the exam. So 11.5, not on exam. But it will be on the quiz that's coming up. So the first thing, I'm going to talk, there are two parts in this section. The first thing is called alternating series. So an alternating series, it just means that the sign alternates, positive and negative sign. And obviously the value could be different too. So for example, you might have a series that's negative 1/2 plus 2/3 minus 3/4 plus 4/5. In this infinite series. So the sign going from negative to positive and then positive to negative, and obviously, right? So you can see that. And then we can write it using a formula. The formula, the sigma notation will be just -1 raised to either n or n plus 1, depends on what you pick as a starting n value. So if we pick n from 1, so that the power of the -1 was dominating the sign change, right? So we begin with the negative, so we can just see it's -1 to the n, because when you put 1 there, you get negative. When you put 2 there, you get positive. That matches with the sign in the series. And then multiply with the actual value, which is 1/2, 2/3, 3/4, 4/5. So those, you can write it as, the numerator is like a 1, 2, 3, 4, so that will be n. And the denominator is 2, 3, 4, 5, so that's like an n plus 1. So that's just the sort of the sigma notation for that series. For alternating series, you always have a -1 raised to some power. It could be -1 to the n plus 1. Multiplied by something, or you could have -1 to the n minus 1 multiplied by some, or you just have -1 to the n. But that will decide whether it's whether you begin with a positive or begin with negative. For alternating series, there's something called the alternating series test. It's a test that only useful when you have alternating series. So suppose we have an alternating series I'm just going to use this form. Let's just say the alternating series, it's sigma n from 1 to infinity, -1 raised to the n plus 1. I want to begin with a positive, but it doesn't have to begin with positive. It could begin with negative. So this could be n plus 1 or just n. And the bn, which is the formula that gives you the individual terms, that's equal to b1 minus b2 plus b3 minus b4 plus b5, and you see the pattern there. So this is the alternating series with bn is going to be greater or equal to 0 all the time for all n. So if the first one, so there are two conditions, we have to meet both. So if the first one, limit n goes to infinity, bn equals 0, and in red, so this is n, not all, so you have to satisfy both. And then the second condition, bn is greater than equal to bn minus plus 1. So this tells you that if bn is greater or equal to bn plus 1, that this term is bigger than the term that's coming after it. So that means the series is decreasing. I mean, the value of bn is decreasing. So if we just look at bn as a sequence, it's a decreasing sequence. If both are true, then the alternating series is convergent. That's what this series says. So kind of just try to explain it a little bit. So when we have an alternating series, we sort of put aside the -1 term, the -1 raised to the power, the -1 term. We only look at the Bn formula, and we take the limit of the Bn, and then we try to find out if the sequence of Bn is decreasing. So we basically find out whether Bn is greater or equal to Bn plus 1. If both are satisfied, then that series is convergent. I personally think this test is a little bit easier to apply than the previous one. You might disagree, but let me give you an example. Let's just take the example that we have above there. So is the example -1 to the n over n plus 1 convergent? This is n or divergent, right? That's the one that we're given. So the first thing I'm going to do is I'm going to identify Bn. So identify Bn, which is, if we just put away the -1 to the nth power and just focus on this Bn, so that's equal to n over n plus 1, right? That's what Bn is. So the second step, so step 1, step 2, is that we're going to try the two conditions. Let's start with the limit and then look at the second condition. Both have to be satisfied. So let's look at the first condition. So limit n goes to infinity of Bn, which is limit n goes to infinity of n over n plus 1. And if you're familiar with this, you immediately know what the limit is, right? So the limit as n goes to infinity, obviously we can take a long way by divide by n in both denominator and numerator. So that just becomes 1 over 1, 1 from the numerator, and denominator is 1 plus 1 over n, but as n goes to infinity, we just have 1 over 1, just 1. Right, so that's a limit of Bn. And this 1, but if you go back to the test, it says that the limit has to be 0. Right, but here we found out the limit is 1. So this limit is not equal to 0. Right, so the first condition already is not satisfied. We don't have to go to the second condition. So since the limit of Bn as n goes to infinity is not equal to 0, so this test doesn't help us to make a sorry, this test, because the first condition is not met, so this test tells us that the series is not convergent. So since this first condition is not satisfied, therefore the series is not convergent. It is divergent. Because we need both of them, we need the conditions, both conditions to be satisfied in order to be convergent. If one of them is not satisfied, then it's not convergent. Questions on this example?
It's not on this example, it's on the one before, but what is that V with the line through it and then N mean? above?
Say it again.
It's BN. What does the V with the line through it N mean? Oh, okay. Aiden just said it.
Oh yeah. Sorry. Oh yeah. Thank you. Yeah, it's for all. So if you I'm sure a lot of you will continue to take math, right? So this notation means for all. Sometimes people just write like this. It's an upside down A, and this sort of like not this one, sorry, this one. This means exists. So there might be some statements say like, there exists. So it's such, right? Epsilon, that means exist. And ST means such that. Those are just abbreviations. But yeah, for all n. Yeah, thank you. So any questions about this example? It's so I'm going to give you another example. So the second example is that we want to know if this series, again, I'm going to just pick n from 1 to infinity. It doesn't really matter what n begins. It's -1 to the n. I'm going to choose n plus 1. It doesn't matter there. We have n over n plus 1 squared. So a little bit different. Now the denominator is being squared. The numerator is still n. We want to know if this is a convergent or divergent. Okay. So the first step, just like before, we're going to identify the Bn. Bn is just going to be the part that after we put aside the -1 to the power, so the remaining, the n divided n plus 1 squared. So that's Bn. You can expand it if you want, or expand it later, doesn't matter. So that's n over n squared plus 2n plus 1. So that's Bn. And the first condition that we want to take the limit as n goes to infinity to see if that's going to be 0. So we want to know if the limit n goes to infinity of Bn, that's limit n goes to infinity of n over n squared plus 2n plus 1. That's obviously, to do it correctly, you divide by the leading term of numerator and denominator and try to take the limit after that. If you do that, I'm going to divide by n squared to all terms. So I get n over n squared over n squared, right? Plus 2n over n squared and plus 1 over n squared. You can simplify a little bit, and it turns out that the numerator is 1 over n, but as n goes to infinity, we get 0. So we end up with a 0. Okay. So what this tells us is that the limit of Bn is equal to 0. So that first condition in the test is satisfied. But that's not enough. We have to show that the second condition is also satisfied. We have to show that the Bn is greater or equal to Bn plus 1. So the third step is that we need to show Bn is greater or equal to Bn plus 1 before we can make the conclusion. Well, I have Bn, which is n over n squared plus 2n plus 1. And then Bn plus 1, and decide what's the easiest way. You know what, let me let me go back to the previous form. I think this is a little bit, it's the same. So this is an n plus 1 squared, and a bn plus 1, that will be just change n to n plus 1. So that will be n become n plus 1. And in the denominator, we have n plus 1, but bn plus 1, that will be n plus 1 plus a 1 squared. So that's a bn plus 1. The n become n plus 1. And then that becomes n plus 1 divided by n plus 2 squared. Can you just sub a number and then another number plus 1? You could, but I don't like, I mean, that's obviously it's a shortcut, right? If you just pick n equals 1 or 2 and then compare those two numbers, that's a quick way, right? I personally, that is not always correct. I think I showed you one example a while ago that if you just want to compare sequence, that may not be correct because you might end up finding the first term is bigger than if you pick n equals 1, right? You might find out that b1 is greater than b2, but then the value might increase, and then at some point the value will be big enough so that b2, like let's say b10 here, so b1 is actually what I'm trying to say is that you have to be careful. If you just compare like two specific terms, it might not be enough to show that the whole sequence is decreasing. Because you might have a sequence that decreases but then increases, right? So I think I show you one example with quadratics. We have to show for all n the sequence is decreasing, not just for one. So be very careful with that. So the next, I'm just going to find the difference. I'm going to find bn minus bn plus 1. So that will be n over n plus 1 squared minus n plus 1 over n plus 2 squared. And then I'm going to try to find out whether this is a positive or negative, because that will tell us whether the bn is bigger or smaller than bn plus 1. So now I'm going to come in denominator. So n plus 1 squared times n plus 2 squared. And then the numerator, the first one becomes n times n plus 2 squared minus the second numerator is just n plus 1 times n plus 1 squared. So it's n plus 1 cubed. And the denominator, not much we can do, right? It's but 2 squares, it's always going to be positive denominator. And I want to know if the numerator is positive or not. So the numerator, I'm going to use the blue color there. I'm just going to work on the numerator, expand the numerator there. So that will be n times n squared plus 4n plus 2, and then minus n plus 1 cubed. And if you expand n plus 1 cubed, so that's n cubed plus 3n squared plus 3n plus 1. That's a formula to remember that, or you can just expand it. If you're interested, I can tell you what that is. And then that will give me just a numerator. So this arrow just means numerator terms. So that's an n cubed plus 4n squared plus, oh, I think that's a 4, not a 2. 2 squared 4. Sorry, that's a 4 plus 4n minus n cubed minus n 3n squared minus 3n minus 1. So just the numerator becomes n cubed cancels, 4n squared minus 3n squared becomes n squared, 4n minus 3n becomes just positive n, and then we minus 1. So that's the numerator. So we end up with the numerator being n squared plus n minus 1. The denominator is n, anyway, denominator is positive. Right. So is the fraction positive or negative for n is from 1 to infinity? So for n is from 1 to infinity, is the numerator positive or negative? Well, n squared plus n minus 1, the smallest value is when n equals 1. When n equals 2, it increases. So when n equals 1, we get 1 plus 1 minus 1 is 1. And then when n equals 2, we get 4 plus 2 minus 1, that's more positive. So this term, this expression is always positive. So the numerator is always positive for all n greater or equal to 1. The denominator is already positive, therefore the difference is positive. If the bn minus bn plus 1 is positive, so we can conclude that bn is greater or equal to bn plus 1. It's actually strictly greater than, but we just write bn greater or equal to bn plus 1 without paying attention to the details there. So that's the second condition is satisfied. So now both conditions are satisfied, and this is an alternating series. So from the alternating series test, if both conditions are satisfied, therefore this series is convergent. Therefore, this series, which is n over n plus 1 squared with a negative 1 to the n, what did I say? It's n plus 1 is convergent. This is for n going from 1 to infinity. So that's this alternating series test. Questions on this? So problem like this, if you have the series, two things, right? One is find the limit. The other one is to find out whether the value of the terms in the sequence decreases. All right, the next example I have is series cosine n pi over square root of n, or n going from 1 to infinity. So this one looks like the series is not alternating because it doesn't have negative 1 to a power, right? But if you expand it, it actually has the alternating sign, because if we put 1 there, we get cosine pi over square root of 1. If we put 2 there, we get cosine 2 pi over square root of 2, and then cosine 3 pi over square root of 3, and the cosine 4 pi over square root of 4. And the cosine n pi itself is it's equivalent to negative 1 raised to a power. So this is like a negative 1 raised to some power there. But you have to decide whether it's n or n plus 1 or n minus 1, depends. Well, usually just 2. Like, it could be even or odd. It could be beginning with positive or beginning with negative. Cosine pi is negative 1, so we get negative 1 over square root of 1. Cosine 2 pi is positive 1. and then cosine 3 pi is -1 again. So you have negative, positive, negative, positive, and it continues. So this series given is equivalent to, if we rewrite it using a -1 raised to a power, -1 to the n, because we begin with a negative, 1 over square root of n. So they're equivalent. And now if we have this familiar form, we can identify the Bn, and then we can take the limit. You can test that first condition, and then we can work on the second condition. So I'm going to do it quickly here. So the first condition, this will be, so Bn, we found it, and the first condition is to take the limit as n goes to infinity of Bn. Right, this is, if you're familiar with this is fairly straightforward. If n goes to infinity, the denominator goes to infinity, but the overall goes to 0. So that's good. The first condition is satisfied. The second condition is that we need to find the difference. So Bn minus Bn plus 1, that will be 1 over square root of n. That's what Bn is, minus Bn plus 1. So that's 1 over square root of n plus 1. Let's common denominator again. So that's a square root of n, square root of n plus 1. The numerator is square root of n plus 1 minus square root of n. And I'm not going to do too much here because I think it's straightforward. The denominator, this is positive, this is always positive, so the denominator is positive, right? The numerator, you have 2 terms subtracting 2 square roots. Well, which one is bigger? I mean, is the numerator going to be bigger? Is it going to be positive or negative? Well, we know that this part is always bigger because of the expression in the radical. It's always in the radical notation. It's always bigger. So n plus 1 is always bigger than n. So n plus 1 is always bigger than n, and the square root of that is always going to be bigger because they're positive, right? So you don't have to worry about negative. So therefore, the numerator is always going to be positive. So overall fraction, it has a positive. Therefore, Bn is greater than or equal to Bn plus 1. It's strictly positive, but I'm just going to put an equal sign there. So from here, both conditions are satisfied. Therefore, the series is convergent. So those are the conditions that you have to check. Questions on this example? So I'm not hearing any questions. I know again, I know there's a lot of material that's confusing and new, but definitely read the book, read the examples and the notes, and try the exercise. I think you're going to be okay. So the next part is absolute series. So let me just write down the absolute series example. So if you have a series with the terms in it are absolute values of an, n from 1 to infinity. If you expand it, become absolute value of a1 plus absolute value of a2 absolute value of A3, and so on. So this is the absolute series, absolute value series, right? Accurate. And here's a definition. This is a new term that it could be really confusing to you, but let me write down first. So a series, so a series just an without the absolute value, a series of an is called absolutely convergent. So this is different. This is not just convergent, it's called absolutely convergent. Boxes. If the series of absolute values, this series with the absolute value of an converges. So that's a definition of absolute convergent, absolutely convergent. It's a new term. You kind of have to remember the phrase together. So what this one says, let me just rewrite the definition. So if the series with absolute values of an converges, then the series an without the absolute value sign is called absolutely convergent. So the one I write in blue, and then the definition above, they're the same, the equivalent. So if the series with absolute values converges, then that series is called absolutely convergent. There's a second definition. A series an is called conditionally convergent. So it's not absolutely convergent. If an, the series an is convergent, but the series with absolute values is divergent. So that's the second one. So that's called conditionally convergent. That's also not in this textbook. It's called weakly convergent. So being convergent, there's a few different cases, and obviously divergent. Right? So that's that one. I'm going to give you a couple examples, try to explain this a bit more. For example, if we consider the series from 1 to infinity of -1 to the n divided by n squared. This one, I'm going to rewrite it. So that becomes n from 1 to infinity, -1 to the n times 1 over n squared. If we just consider this is the alternating series, right? We can try to figure out whether it's convergent or divergent. And it turns out that if we try to follow the alternating series test, this one is convergent. But let's try to take a different approach by looking at one of those definitions, the first one. So what I'm going to do is that I'm going to take this series given, doesn't matter which form, and I am going to find the absolute value of the formula inside. So consider the series with absolute value of -1 to the n, 1 over n squared, and from 1 to infinity. We're just going to add the absolute value sign. And then if we have absolute value sign, and then we can take the absolute value of -1 to the n first. So absolute value of -1 to the n times absolute value of 1 over n squared of n from 1 to infinity. And the benefit of adding absolute value is that this -1 to the n with absolute value sign is always going to be +1, right? Doesn't matter it's positive or negative, but when you add absolute value sign, so this is always going to be +1. The second absolute value, well, n is already positive. So when you add a new absolute value sign, it doesn't make a difference. It's still going to be +1 over n squared. So that series with the absolute value, it just becomes a series of 1 over n squared, and from 1 to infinity, right? And if we do the p-series test, the p is 2 here, it's more than 1, so we know that this series is convergent. Right? So what we conclude by, so what we find out just now is that this absolute value series is convergent. We did not figure out whether this given one is convergent or divergent, right? We didn't do that in this part when I add the absolute value sign. I just look at the sequence, the series with the absolute value sign in it, and I found out that that part is convergent. Going to the definition we had, it says that if the series of absolute values, if that's convergent, then the given one without the absolute value is called absolutely convergent. So here, so we found out that the one with absolute value sign is convergent, therefore the given one. So this series without the absolute value sign is called absolutely convergent. So that's what this series is. You probably wonder, is this still going to be convergent or divergent? Well, if it's absolutely convergent, it means it's convergent. So that's a theorem that I'm going to write next. So if a series is absolutely convergent, then it is convergent. If a series is convergent, doesn't mean it's absolutely convergent. So this implication going in one direction. So absolutely convergent implies convergent, not the other way. So yes, so this series is absolutely convergent and also convergent. Any questions about this example and the definition? There's a lot to take in here. When I first come across, convergence, absolutely convergent, conditionally convergent, it was confusing. And to be honest, it took me a long time, like weeks, to try to kind of like get my head around this different terminology. But you guys are going to be okay. A lot of you are smart. So any questions about this example? So let me box this because this is the theorem. Now, let me give you a couple more examples. So the next example, let's consider this series, -1 to the n plus 1 times 1 over n. So the previous one, we had a 1 over n squared. But here, this one, I'm beginning with just 1 over n, for n going from 1 to infinity. Right? And for this one, I want to know if it's absolutely convergent. Or maybe it's not absolutely convergent, but is it conditionally convergent? Or maybe it's not conditionally convergent. Maybe it's just divergent. Or maybe we want to know if it's convergent at all, or divergent. So what I'm going to do is I'm going to take take this series, but only consider the one that with absolute value. So consider the series with absolute value, -1 to the n plus 1 times 1 over n. Again, when we add an absolute value, the -1 with a power term, this expression just become 1. And the 1 over n is always positive. So we just, this series of absolute value becomes series of 1 over n. Right? And in this case, p is equal to 1 if we use the p-series test. P equals 1 is not greater than 1, so it's divergent. So this the series of absolute values is divergent. That means it's not going to be absolutely convergent. So the given series is not absolutely, absolutely convergent. But is it conditionally convergent? So conditionally convergent, saying that the given series has to be convergent, but the absolute value of that series is not convergent. So we found out that the absolute value series is not convergent, but how about the given one? Is it convergent? Well, so the question is this series conditionally convergent? Well, we need to know if it's convergent at all, right? How do we find out if it's convergent? Well, that will go back to the alternating series test. So we know it's alternating series, and this is Bn, and the limit n goes to infinity of Bn, which is 1 over n. That's going to be 0. So the first condition is satisfied. How about the second condition? Bn minus Bn plus 1. So that's a 1 over n minus 1 over n plus 1. It turns out that's n plus 1 minus n over n times n plus 1. It's just 1 over n times n plus 1. This, I know for sure, it's always positive for any n greater or equal to 1. So this is a positive. Therefore, Bn is greater than or equal to Bn plus 1. It's actually just greater than, but again, we're going to keep the equal sign there. So the second condition is also satisfied. So which means this series -1 to the n plus 1, 1 over n is convergent. But because of the absolute value, series is not convergent. So since the absolute value of this series is not convergent, therefore the series we had that's convergent, we call it conditionally convergent. It's conditionally so that's a conclusion. It's not divergent. It's not absolutely convergent. It's conditionally convergent. Like as earlier mentioned, like when you study higher level math, when you take some analysis class, you're going to learn something called strongly convergent and or weakly convergent. So that's like a more terminology to learn there. But fun stuff if you really enjoy sort of pure math track analysis. Questions about this example or the example above?
Yeah, I have a quick question. So on the absolute value version, we what am I trying to say? So we found that it was just 1 over n, and then we did the p series. But why didn't we do the p series on the other value that wasn't the absolute value? Like we just straight up made it go to 0 by having the limit n go to infinity.
Oh, in this part, why don't we just directly use the p series test?
Yeah.
It doesn't work because of the so glad you brought it up. So p series test that works if you have just 1 over n to the p, right? That's when you use it. But because here we are given the given series has an extra part, this there's a -1 to the n plus 1, that's an extra there. You cannot move it to the front because it depends on n. So the -1 to the n plus 1 part has to stay with 1 over n for every term. So it no longer satisfies this 1 over n to the p. So if you have -1 to the 1 over n to the p, sorry, -1 to the n or n plus 1 doesn't matter. If you have this expression, this p test doesn't work. So it no longer works in that case. The question. Any other questions? All right. Like I said before, this stuff is not easy to, is different from calculus, right? It's a lot of terminology and the theorems, definitions. It is important to try to understand them because you're gonna feel like, later on when you take a higher level class that's more abstract, you're gonna feel like you're more prepared. So try to understand this. And on that note, I'm gonna let you go. And I'll see you on Wednesday. If you have questions, I'll be around tomorrow during office hours and to bring them to class tomorrow. Wednesday. All right, take care.